In this video, I'm going to show you how to graph the motion of a simple harmonic oscillator. We will plot the displacement of a harmonic oscillator, in this case a pendulum, as a function of time. We'll plot the velocity as a function of time, the acceleration as a function of time, and we'll compare the phase differences between these graphs. We start with displacement versus time. And I'm going to start with the pendulum located at the center of its trajectory. Please remember that just because the pendulum is at the center, which would be the equilibrium position, technically it's never an equilibrium. An oscillating pendulum is not an equilibrium because it always has a net force, the centripetal force. That's the reason why it continues to swing. There is still a net force. So as long as there is a net force acting on an object, that object is not in equilibrium. And this is for the swinging pendulum. All right, so the pendulum is going to oscillate back and forth. It's going to go from zero amplitude, where the displacement is zero, somewhat red for this, where the displacement equals zero here, and it's going to go to its maximum displacement. Then it's going to come back to zero, and then it's going to go to swing up to its minimum displacement and then return to start to complete one cycle. To complete a full cycle, the oscillator has to go to one side, to the other, and back. From one side to the other and back. Amplitude is locations of max displacement. Okay, so watch. Pendulum swings right, comes back to zero, swings left, and comes back, returns. So it's at maximum amplitude at t/4, that's 1/4 of its period. It's at zero amplitude, t/2. It's at minimum displacement or negative amplitude at 3t/4, returns to starting position for a full t. So this is one complete cycle, one up and down, one back and forth swing of an oscillation on this curve. If I want to denote the radians or the angles through which this occurs, at t/4, that's pi/2 radians. t/2 are pi radians. 3 pi/2, at 3t/4, that's 3 pi/2 radians, and one cycle is a full 2 pi radians. Okay. This displacement versus time curve can be defined by S of t, displacement as a function of time, equals a sine omega t. Omega is the angular frequency. Angular frequency is 2 pi times the normal frequency. We'll be generating a velocity versus time graph from displacement versus time. If you look at the plot that I have, this is still displacement versus time, and it's governed by this equation, S of t, displacement as a function of time, equals a, the amplitude, times sine omega t. Omega is the angular frequency. Omega has the equation 2 pi times f, where f is frequency measured in hertz or reciprocal seconds. So to generate velocity versus time graph from displacement versus time, you look at points on the graph where you have maximum amplitude right here, zero amplitude. Look at the minimum amplitude and again zero amplitude or zero displacement. And you shift these points to the left by pi/2. So right here where I have a maximum amplitude at t/4 for displacement versus time, that maximum amplitude will occur right here for velocity versus time, right at zero. When I have zero displacement, no amplitude, that occurs halfway through the period for velocity, for displacement versus time. Well, for the velocity versus time graph, that point is going to be shifted. It will occur right here. I keep going. Look at where the minimum displacement occurs for displacement versus time. That's at 3t/4. I'll shift that to the left, so that minimum amplitude will occur right here at t/2. Coming up, I look at a full one complete cycle. I'm back to no amplitude, zero displacement for the displacement versus time curve. That is going to occur at 3t/4 right here for velocity versus time. And then I can complete the cycle for velocity versus time by drawing the next point that would come back up to maximum amplitude. So what the graph ends up looking like, you draw the points first and then you connect the points with a smooth curve. The graph will look like this. This is the derivative of displacement versus time. Now I slide the red graph to the left. This is phase shifted now by pi over 2 and complete the line. Displacement versus time, the time derivative of that is velocity versus time. So you can see, taking the derivative, if my displacement versus time function is a sine omega t, the derivative of sine omega t is cosine omega t, the derivative of sine is cosine, and then I multiply cosine omega t by the derivative of what's inside the function. The derivative of omega t is omega, so you'll see now I have this term. Velocity with respect to time, velocity as a function of time equals amplitude times omega cosine omega t. So this blue graph, it really doesn't come to the same height as the displacement versus time graph, but that's okay. IB just expects you to be able to draw the shape in general. Now I could find the maximum velocity. The maximum velocity occurs where cosine is 0. When cosine is 0, it occurs at cosine of 0. At cosine of 0, that has a value of 1. The maximum velocity then is the amplitude times the angular frequency. That's really convenient. This is more an HL topic. This is topic 9, but you can see it still works for SL physics. It's a good review. Cosine leads sine by pi over 2. Velocity leads displacement by pi over 2, or 1/4 the period. Why do we say that? Because cosine has a max at 0 where sine has a min at 0. Alright, so we'll be drawing acceleration versus time. You can see I have the velocity versus time curve still drawn. And just note, because I made this curve in PowerPoint, I couldn't get it to line up perfectly right here, so that's why it looks like that. It should be a complete, the amplitude should occur right over 2 pi, but it doesn't because I couldn't draw this perfectly. Anyways, okay, so just like we did last time, we're going to look at these points on the curve where I have minimum or no displacement, minimum displacement, no displacement, maximum displacement. I'm going to shift these points to the left by pi over 2. So for my acceleration versus time graph, where velocity has no displacement at t over 4, 1/4 of the way through the period, that no displacement is going to occur right here at 0. When we have minimum displacement for velocity versus time halfway through the period, that is now going to occur at t over 4, so I'll draw a dot right there. I draw the dots first and then I end up connecting the lines. At 3 pi over 2, my velocity versus time graph has, again, no displacement, no amplitude, so that's going to be shifted to the left for my acceleration versus time curve, where it has, again, the maximum amplitude at the full cycle. That's going to occur at 3 pi over 2, or 75% of the way through the period for acceleration versus time. And then to complete the cycle, I just draw the dot needed. Now I'll connect these lines, smooth curve. This will now be my acceleration versus time graph. It's shifted to the left by pi over 2. You can see I slide this over and I just complete the curve. Again, it's not perfect. So the time derivative of displacement is velocity. The time derivative of velocity is acceleration. So the derivative of cosine omega t is negative sine omega t. Then I multiply the function, the original function, by the derivative of what's inside the trig function. So the derivative of omega t is, again, omega. So I multiply a omega by an additional omega. So this is negative a omega squared sine omega t for the acceleration versus time curve. When we have maximum acceleration, sine equals 1, so that's a sine of 90 degrees or sine pi over 2. Maximum acceleration is equal to negative amplitude omega squared. Again, this is for topic 9, but it's still helpful for SL physics, especially if you're reviewing derivatives. Negative sign leads cosine by pi over 2. Acceleration leads velocity by pi over 2, or 1/4 the period. And acceleration leads to displacement by a full pi, or 1/2 the period. We'll see this summarized on the next slide. And note, for all of these graphs, I have no additional phi term. There's no initial phase shift, and that's just for simplicity. As you get into more advanced analysis, for example, my displacement versus time, my displacement graph will look like a sine of omega t plus phi, and that phi would just denote an initial phase shift. For simplicity, I don't include that. All right, so hopefully you've been drawing along, and if you haven't, go back and watch the video, but this is to summarize. Velocity is the time derivative of displacement. Acceleration is the time derivative of velocity. Functions lag their derivatives, and acceleration and displacement are opposites of each other. Look at this. Where I have my displacement versus time curve, look at how the acceleration versus time curve looks. It's like this. If I draw this up here, they're totally opposites of each other. That is out of phase by a full pi. Velocity is out of phase with displacement by pi over 2. So this graph is shifted to the left by pi over 2 to generate the velocity versus time curve. For acceleration, this graph is shifted to the left by pi over 2, or 1/4 of the period. IBO expects you to draw the phase differences for simple harmonic oscillators. Let's say during the exam you forget whether or not to shift it to the left or to the right. Fortunately, you won't lose points for that. All you need to know that it's out of phase by pi over 2.